All right, good morning. Happy Thursday. It's not quite Friday, but we're getting there. Yesterday we looked at a mass oscillating on a spring in a horizontal orientation. This is the best I could do to recreate a spring here in this software. I'm not going to bother to draw this mass in multiple locations with the spring. Okay, it's going to get too messy and too difficult. But I want to point out to you that there are three important positions here that we're talking about in regards to the location of the mass on the spring. So when it's in the position that I'm just fiddling with right now, the one on the right, that spring would be stretched out. And when it's in the one at x equals 0 in the middle, it's stretched out, but not as much as it is when it's on the right. And I'm assuming here that we're defining the location of the mass. These are all x's that I've got down below the axis. I'm defining the position of the mass to be the center of that mass. So yesterday I think I put an arrow on your diagrams, right? The point I want to make is that mechanical energy is conserved everywhere in this situation because there's no friction. This is what we're dealing with in all of these problems. And what that means is that the potential energy, the elastic or spring potential energy that the mass has at that position is all of the mechanical energy, because at that position it has to stop momentarily, which means it has no kinetic energy there. On the other hand, at this position, it has kinetic energy, it's moving as fast as possible, but since it's at x equals 0, it's at the equilibrium position, Hooke's law will predict 0 newtons of force. And I don't mean to make it sound like it will predict it. Hooke's law says, correctly, there will be 0 newtons of force acting on the mass at that point. So there's no potential energy. Whereas in this third position, it is moving because it hasn't reached a stop yet, and it's not at the equilibrium position, which means it has potential energy as well as kinetic. And the potential energy it has in this first position and the kinetic it has in that middle position I've drawn and the kinetic and potential it has at any other position are going to be the same. So you're using conservation of energy to solve these problems. Again, though, you're not using conservation of energy to solve every problem, right? Because as we saw yesterday and somebody asked this morning, for question like 5 or I think even 6, you don't have to set up any equation. You're just using the potential energy of the mass is 1/2 kx squared. Right? In question 6, you're given k, you're given the displacement at a particular point, and it's how much energy does it have? Potential energy. Well, you use the formula. So it isn't always this grand epic journey of setting energy equal to energy, but often it is. So does anybody have any questions you would like me to go over here from that lesson yesterday? Go ahead, Melanie. Number 9? Okay. A question that's disguised in a certain way. That's what number 9 is. If I asked you how much potential energy is stored in a spring if I compress the spring 3.5 centimeters, you would answer the question by saying, well, the potential energy stored is equal to 1/2 kx squared. Right? And you know k and you know x, and you can put the numbers in. But that's the work done in stretching it to that point. Because if I take a spring, so here's a spring, and let's just imagine it's 75 newtons per meter. This spring is not, but I stretch it 3.5 centimeters, and that's clearly more than 3.5. I have done work in doing that task, right? I've applied a force over a distance to get it to this state that you're looking at. But that means that the work I did went somewhere. And where did it go? Elastic potential energy. So if we calculate this, this will be the answer. Does that make sense? Okay. I want to just throw out 2 other quick questions here to drive this point I'm making with question 9 home. if I said that we lift it doesn't matter what the mass is, a 6 kilogram mass for meters, and then over here I say we throw a baseball. I have no idea what the mass of a baseball is. We throw a 0.3 kilogram ball at 12 meters per second. I've got two statements here, right? If I said, how much work was done in each of these cases, it would be a mistake for you to start thinking work is force times displacement. I mean, that might be helpful here with the problem on the left, but it's a dead end with the problem on the right. The bottom line is the work done in both of these cases is the change in energy of the system. So all I have to do to find the work done here for the 6 kilogram mass being lifted is find its potential energy. All I have to do to find the work done in throwing this ball at that speed is find its kinetic energy. All I have to do in question 9 to find the work done is calculate the potential energy. Does that make sense? Okay. Other questions from yesterday? Yeah.
Question
10? So a 75-gram object is in simple harmonic motion, which means it's a simple harmonic oscillator, which means everything we've talked about is true. The energy is conserved, mechanical energy is conserved, the force varies, the acceleration varies, all of that stuff is true. We're given the spring constant and you're told the maximum displacement and you want to know the maximum acceleration. So again, it doesn't have to be this epic problem where you're going to set energy at one place equal to energy at another place. If we look at what maximum acceleration is about, why would we get a maximum acceleration? Well, we would get a maximum acceleration because we have a maximum force acting on the mass. And I don't know what I want to put for a subscript here. Like I could put Fs, I could put F net, I could put F restoring. It doesn't matter because it's all one force. I'm going to go Fs because that's, I think, what we're going to have to do here to answer the question. So when do we get a maximum force that the spring exerts on the mass? Well, it happens when we get a maximum displacement. I mean, what I'm getting at here is F equals ma. So if you want the biggest acceleration, you need the biggest force. But the force equals kx. So if you want the biggest force to get the biggest acceleration, you need the biggest displacement. But you're told the maximum displacement. So if we take the maximum displacement times this spring constant, we are going to get the maximum force. And if we then divide that maximum force by the mass, we're going to get the maximum acceleration. Now, before I finish this problem, some of you might have taken a different approach here and said, this requires maybe a little more thought, it's more conceptual, that the maximum acceleration occurs here. But now that I think of saying that, I think in order for you to understand the maximum acceleration occurs there, unless you're just memorizing that, you have to go through this process again and say the displacement is as big as possible, so the force is as great as possible. I suppose you could say the acceleration is as great as possible because the spring is pushing back most there, but that's equivalent to saying the displacement's as big as possible, away from the equilibrium position. Anyway, are you fine, Ethan, with me just doing this on my calculator? Okay, so what would we get for the maximum force? we would have that spring constant of 5 newtons per meter times 0.08 meters. So this is the maximum force, 0.4 newtons, and that is a force that's the spring force, which is the restoring force, which is the net force, which is equal to ma. So if I divide that by the mass of 0.075, I get 5.3 meters per second squared. You okay with that? Okay. Any other questions?